All right, today we want to move on from techniques. We've got our two major techniques. We just need some time to practice them. We got integration by substitution and integration by parts. Anti-chain rule, anti-product. So we're building up technique, and that's great. But we've got to think about what's integration for. So what's integration for? The answer is still the same as it was at the end of top one. Integration is multiplication, but one of your factors is continuously variable. That's the big change. That's what's going on with integration. So the way we get at that is these weird area problems. So we're going to ask, what's the area of this triangle? And you're all going to say 7.5, 1/2 base times height, because you've been programmed with that shortcut for finding area. So the answer is not 7.5, because that's the reason that we're finding the area of this triangle using too much math is because we know where we're headed. If we do some weirdo shape and find the area, because the only way to find the area is through integration, then it doesn't ground the process. Take something simple where you know what the area is supposed to be, apply the process, see if it returns the result that you expect. So that's why it's find the area of the rectangle, find the area of the triangle, find the area of the circle. But we're restricting ourselves. There is only one area formula, because it's the only area formula we need, because now we're all armed with calculus. And that's area is equal to length times width. So we're not doing this process to find the area of the triangle. We're doing this process so that we can understand the process. So what we want running in the background, I want you to think about integration is multiplication, but one of the factors is continuously variable. Integration is multiplication. But one of the factors is continuously variable. I usually say one of the factors is variable, but the part that makes this a calculus problem is that one of the factors is continuously variable. If we just have a bunch of stuff that we're trying to add up, if it's all the same, that's when we get to use multiplication. If it's all different, then we just do addition. And that's kind of what happens here. It's like, well, one of the factors is variable, so I'm going to make it constant so that I can use multiplication. So here's what we're going to do. Area is equal to length times width. Everything we see is rectangles. Everything that we see is just a bunch of rectangles. We're going to have to start looking at this like we're a computer processor. We're the graphics card. All we see is rectangles. I know when you look at your computer screen, it looks like it has all these fancy curvy lines. All that you see is rectangles. Everything is just a pixel. It's hard to think about now that we have smartphones and we can't see individual pixels. So think about your Game Boy, where you could see the individual pixels that make up the picture. Everything is that now, because all we have for area is length times width. Everything is rectangles. So this triangle is not a triangle. I just happen to be using a very high resolution, and it makes these sides look smooth and linear, but I assure you they are not. All the way up and down this triangle we actually see rectangles. Now, this is not exact because we've zoomed in, or we're zoomed really far out. So the rectangle is vertical, these sides are angled. But if we zoom in close enough, this isn't going to change that much. So the area of this triangle is just a bunch of rectangles stacked on top of each other. It's not an adult human. It's 3 kobolds in a trench coat. That's all it is, just stacks of things. So I have a length and a width. Doesn't matter which one we call what, but we have a width and a length. Now, what's going on is that the length that I've labeled here, the little height of that rectangle, is too thick. The stack of rectangles, they're not that thick. They're actually thinner. The thinner we make these rectangles, the thinner we make each of those rectangles, the more like a triangle this looks. So we're stacking up a bunch of rectangles. The thinner the rectangle, the more the stack of rectangles looks like a triangle. Thinner rectangles makes our stack of rectangles look more like a triangle. Questions? All right. So that's the first step. We got to view this triangle not as a triangle, but as a bunch of rectangles. I need this space over. So what we're going to do is we're going to calculate the area of this triangle by calculating the area of all those rectangles. We're going to add up all those rectangles. We're going to assume that instead of the width being different at the bottom and at the top of the triangle, that for some small change in height, the width is constant. That's the assumption. That's what we want to happen, because integration is multiplication, but one of the factors is variable. That's the problem right there. So I make one of the variable factor constant for a little while. So we have to start naming things. Notice that we said thinner rectangles will make the stack of rectangles look more like a triangle. So I want that length that I labeled L. That's the part I want to make thinner. That's how we increase the resolution. So that whatever dimension we're going to make thinner, that one we're going to label with the delta variable. So this is going to be delta x. So delta x is going to be the thickness of that rectangle. It's the length of the rectangle. So the area of that one rectangle is length times width. So the length is going to be my delta x. We also need to write the width in terms of x, because as we saw in substitution, we can't integrate w with respect to x, especially if w is some function of x. We got to write w as a function of x so that we can integrate it. So I need to write w in terms of x. So at this point, we need to write w in terms of x. That means that we need to define an x, because notice that my picture has no x in it. The important part about defining x is that it has to go in the same direction that your delta variable is getting thinner. Delta is squishing the height of this triangle. So that says your x variable has to be an up and down variable. It has to be labeled somewhere vertically. On the problem on the homework, it was labeled from the base of the triangle up to the rectangle. So we're going to say x is the distance from the base of the triangle up to the rectangle. There are infinitely many places we could have defined x. All x had to do was be some kind of vertical variable. We happen to define it from the bottom of the triangle up to the slice. Another reasonable place to put it would be from the top of the triangle down to the slice. Here are the things that happen. You have the slice, your rectangle, and once you define x, one end is the slice, the other end is where the variable is equal to 0. One end is the slice, the other end is 0. So here, down here at the base of the triangle, that's where x is equal to 0. Furthermore, in this case, we have defined up to be positive. One end is 0. Put the slice in the positive direction. You don't have to do it this way, but you're just going to make things worse for yourself if you arbitrarily decide that up is always positive. So this is the positive direction. Once we decide where 0 is in the direction of the slice, that's the positive direction. So when we get to the top of the triangle, that's where x is equal to 5. This is a choice that we made. We decided where to put the variable. Once we decide where to put the variable, that determines where x is. That determines what the positive direction is. Now we can write W in terms of X. What is the width of the rectangle that is X units above the base of the triangle? We can see by the sides that this is going to be a linear function because it's going to be, we have similar triangles running around. That means things are in proportion. Proportions are linear functions. So when X is 0, notice that the width of the triangle is 3. When X is 0, the width is 3. And when X is 5, W is equal to 0. So the width in terms of the height above the base X, W starts off at 3 and will decrease by 3 in 5 units. So I'll make a linear function with a slope of -3/5. When X is 0, the width is 3. When X is 5, the width will be down to 0. So that's the area of one of these rectangles. I've got a width and we've got the height. So we can calculate the width based on the height above the base of the triangle. This is the area of one rectangle. This is the area of one rectangle. So what we're going to do is we're going to break this, we're going to view this triangle as a bunch of rectangles, and we're just going to add up all those areas. So we're going to take our area. And I'm going to subscript because I'm going to count. Here's the 0, the first one, the second rectangle, third rectangle, fourth rectangle, and we're going to have a bunch of rectangles. So it's going to be subscripted. There's the length, the width times the height, which is delta X. And we're just going to add up all these rectangles. So we're going to take the sum as I goes from 1 to n. We're counting the rectangles. First rectangle, second rectangle, third rectangle, all the way up to the nth rectangle. Then we apply calculus. Since we have observed that more rectangles gets us closer to the actual area, we should use more rectangles. And in calculus, being the study of infinity, we're going to use infinitely many rectangles. This caused a lot of problems. This is a very difficult idea back when we first started thinking about these things. Because if we have an infinite number of rectangles, doesn't that mean that the width of each rectangle or the height of each rectangle is 0, and so the area is just 0? How could doing more result in no area? And so I imagine all the mathematicians were sitting there thinking about that. And I imagine this smoke-filled room, and they're just like hitting bongs. I go, but dude, wait. If we have an infinite number of rectangles, then they're going to have a height of 0. And they're just like a bunch of these stone frat boys trying to figure out how infinity works. You know what I mean? We always credit Newton and Leibniz for coming up with calculus as we know it today. And Newton went crazy. He's like, oh, calculus. And he releases his book. And they're like, oh, great, what are you going to do next? He's like, oh, forget that. I did my thing. You know what I mean? Imagine if you were, if all you have, it's like being a one-hit wonder, but not being thought of as a one-hit wonder. You know, like Einstein. Einstein's like, oh, relativity. And we're like, oh, that's awesome. What's next? He's like, oh, fuck off, relativity. Is that not enough? Are you not entertained? So I was wondering about that. It'd be like making one hit album and then just disappearing. It's like, oh, that was good enough. Anyway, what are we talking about? Oh yeah, Newton and Leibniz. So then we're going to do the calculus thing. This is the calculus thing. Use an infinite number of rectangles. In what we call a Riemann sum. It's just a bunch of length times width. This is how we cope. Well, before this limit as n goes to infinity, this is us dealing with multiplication, but one of the factors is variable, but discretely variable. We can break it up into rectangles. This is us dealing with one factor being continuously variable. We make a Riemann sum. And then we end up with our integral. No longer subscripted because it's a continuous variable now. So instead of my discrete delta x, I have a continuous dx. Now we just have to add up all the x values where we have a rectangle. The rectangle started off at the bottom when x is equal to 0. And the rectangles stop when x equals 5. Now, if everything worked out okay, this should give us 7.5, which is what we know the area of the triangle should be. So let's see, 3x minus 3/10 x squared evaluated from 0 to 5. So we're going to have 3 times 5 minus 3/10 of 5 squared. Notice we'll cancel out one of the 5s. So I'll have 5 times 3 is 15. Cancel out the 5. Cancel the 5 out of the 10 to leave it 2. 15 divided by 2 is 7.5. 15 minus 7.5 is 7.5. So everything works out. Yes. Yes, I need to describe the width of this triangle as a function of the height above. So I noted down here where x is equal to 0. This is our choice. We just say when x is 0, the width is equal to 3. When x is 0, the width is equal to 3. And when x is up here at 5, the width is 0. So if we want to go from, if we want to start off at 3 and get to 0 when x is equal to 5. So we start off at 3, we subtract 3, but make that take 5 units by dividing by 5. So We want to think about slope. I want the change in W to be -3, to go from 3 to 0. And I want that to take 5 units. I want the run to be 5. So -3/5 is our slope. Knowing that it was linear, because the sides of the triangle, the sides of similar triangles are proportional, or look at them, they're flat. Yes.
So if the length of the triangle was 7, then it'd be 7.
Correct. And if the width was 4, then it would decrease, it's be 4 minus 4/5 x. Yes.
You always go up from the bottom.
Nope.
So if you're going down from the top, would it be counting 3 or still 3?
Let's find out. A great question. What if same triangle, same rectangle, but instead of saying x is the distance from the bottom of the triangle up to the slice, let's say x is the distance from the top of the triangle down to the slice. Once we decide where x is, one end is the rectangle or the slice, the other end is 0. And the slice is in the positive direction. So in this case, down is positive. The base of this triangle was 3. And the height of the triangle is still 5. So now we're going to write a different function. When x is 0, the width is 0. And when x is 5, the width is 3. 3 is how the width is changing. That's why it's in the numerator. 5 is how the x is changing. That's why it's in the denominator. It's the rate of change of w with respect to x. So it's not going to change to 5/3. It's still going to be 3/5. But notice that in this case, the width started off at 0 and increased to 3. So we are changing the sign of the slope. So here, the width will be starting off at 0 and increasing by 3 in 5 units. We would just write 3/5 x. So now the area of a triangle, or sorry, the area of the rectangle is still width times length. The width in this case is 3/5 x. And the height is now still delta x. So instead of integrating 3 minus 3/5 x, we'll just integrate 3/5 x. And it'll still go from 0 to 5. questions? The important thing to realize here is that we're building a linear function. You want to see the size of that triangle. That's increasing linearly. That's why it's making lines for the sides. We could also go at this problem by thinking about similar triangles, because similar triangles are proportional. However, that allows us to solve the similar triangle problem. It doesn't really expand the problem in general. Because if instead of having, let's say, a triangle with this nice linear function, what if I said it's the triangle has been putting on a little weight, and so now it's shaped like a parabola. We don't have similar parabolas. So if you look at this problem and think only, I'll use similar triangles, you're thinking about this specific problem. You're not thinking about how the problem works. Does that make sense? It's not about coming up with 7.5. We knew 7.5 as soon as I drew the triangle. That's not the point. The answer is almost never the point of math. The reason that we pick a triangle is so that we can do calculus on it and see that the answer comes out to what we expect. That way we can have faith in the process when our sides stop being nice and linear. When this side is like a parabola and this side like just goes, whoa. Yes. Yes, if this was the side view of a cone, we would apply the same principle, but instead of this being a rectangle, this would be the side view of a cylinder. Right? Because if we take a coin and look at it from the side, it just looks like a rectangle. But then when we look at it from the top, it's a coin. So if instead of just being if we're looking at this as a cone, then the rectangle that we saw earlier would not be a rectangle. Where we were viewing the triangle as a stack of rectangles, we can view the cone as a stack of cylinders. And so instead of calculating the area of a triangle, we would be calculating the volume of a cone. So we'll calculate the volume of the cone by calculating the volume of this stack of cylinders. And so we'd start by writing down the volume of one of these cylinders. see, the volume of the cylinder is pi r squared times h. Writing pi r squared times h is not doing anything fancy. The way we calculate volume is we take the cross-sectional area and multiply by the height. That's just how we find volume. Volume is just one dimension more, finding length. Area is equal to length times width. Volume is cross-sectional area multiplied by the height. The cross-sectional area of the cylinder is a circle, pi r squared, times the height of the triangle. So to make our volume of stack of cylinders closer to the volume of a cone, we use thinner cylinders. And that's why the height of the cylinder is going to be delta x. That means we would need to write r in terms of x. Looking at this in 3/4 view is difficult, especially because I do not have the ability to draw very well. Not complaining, that was by choice. I decided not to be very good at drawing, so I didn't practice. From the side, there's our delta x, but instead of viewing this as a rectangle with a width, this is still a cylinder with a radius. Once we look at it this way, we can just do the same thing what we did in the previous problem. We can notice that the radius is going to be a linear function of x. We can make x whatever vertical variable we want, but there are only two that actually make sense in the context of the problem. So if x is the distance from the top down to this cylinder, then up at the top is where x is equal to 0. Down here at the bottom is where x is equal to 5. Notice at the top, our radius is 1.5, and at the bottom, is 0. And at the bottom, our radius is 1.5. So our radius in terms of x starts off at 0 and increases by 1.5 in 5 units. That'd be a weird way to write 3/10. So let's not write that 3/10 that way. So this is going to go in for the radius. So the volume of one cylinder is pi times this radius, 3/10 x squared. I just wrote down the volume of the cylinder, pi r squared h. H is my delta variable. Write r in terms of h. Then what we would do is we'd index these and add up with the Riemann sum, then let the number of the number of cylinders go off towards infinity. And we know that that just turns into a definite integral. So the volume of the cone is pi times the radius squared. The delta x becomes dx, and we integrate wherever there's a cylinder. And they go from 0 to 5. Then we can check this against what we know to be the volume of a cone. 1/3 pi r squared. Questions? All right. Of course, no questions. We've run over time. That's going to do it for today. That's going to do it for this week. Everybody have a good weekend, though. See you on Monday. Thanks for playing.
You have a question about that?